As you see, the title. Yeah, as you can see, the title is a little far from the topic of the conference. However, I hope you will enjoy my talk. So I start with short introduction. I present the motivation of my work. Then a few words about scanning thermal microscopy, which I used in my investigations. Then I discussed some thickness doping effects on thermal conductivity and also temperature-induced changes of structure, electrical, and thermal properties. And I present some results of thermoelectric parameters. And at the end, I will discuss the heat transport mechanism. And at the end of my talk, I will present some conclusions. So I agree with the speaker before me. I also like oxide materials. And my talk is today is about oxide thin films. And as we know, thermoelectric material should be a low thermal conductor, along with a high electrical conductivity, high Seebeck effect, high thermoelectric figure of merit, and also thermal power factor. As we see here, these parameters are connected with each other. So the fundamental task is how we can optimize all these conflicting parameters of thermoelectric materials. I mean, the Seebeck coefficient is described by we measure the voltage across the temperature difference. The figure of merit is described by Seebeck effect, Seebeck coefficient, thermal and electrical conductivity and temperature. And we can write it as a power factor, temperature over the thermal conductivity. Another problem is how to measure thermal properties at nanoscale. This task is quite challenging. There are a few methods which allow such measurements, like time domain thermoreflectance, 3-omega method, and also the scanning thermal microscopy. And the last one is quite promising method for thermal conductivity measurements. Another problem with thin films is also the dependence of thermal conductivity on layer thickness, layer structure, and the value is typically a few orders of magnitude smaller comparing to bulk material. And we can find in literature that selected oxide thin films seems to be very attractive thermoelectric materials. They have a lot of advantages, like high chemical and thermal stability at elevated temperatures, and low cost production, non-toxicity, and environmental friendliness. If we look into papers, we can check that the thermal conductivity is typically from about 1 watt per meter Kelvin to about 20-30 watt per meter Kelvin. If we compare it with bulk material, we get almost 80 watt per meter Kelvin. So we see, even if we have the same material in the form of thin film, it possesses a quite different thermal properties. The same, here is the table with some thermoelectric properties of selected oxide materials. It's mainly zinc oxide, indium tin oxide, copper oxide, and some mixed material based on indium tin oxide doped with zinc. So we see that the power factor is around 0.3 milliwatt per Kelvin squared multiplied by meter. So this is the value which we can get from oxide thin films. I used in my measurements scanning thermal microscopy, so I will say a few words about the method. Here you can see some recent papers about this technique. Generally, it's based on typical AFM microscope, in which we have a thermal module, and instead of AFM probe, we put thermal probe. And we have two basic measurement modes. We call it low probe current and high probe current. The low probe current is in other words, a passive mode. It allows for measurements of temperature distribution, and that's why it's called temperature contrast mode. If we apply a high power probe current, we do active mode, in which we measure thermal conductivity distribution. So it's called also conductivity contrast mode. What does it mean, high and low current? I will say a few words about thermal probes. I used palladium probes in my experiments, but there is a very popular group of resistive probes that historically first was the Wollaston wire. Today we have palladium probes and silicon probes. As you can see, they differ in spatial resolution. So the first one has a low resistivity wire, which forms the tip of the probe, but it has quite high sensitivity. In case of palladium probe, the active element is just a palladium resistive pad deposited near the apex, and the spatial resolution is better than 100 nanometers. And the last type is a U-shaped conical silicon probe. This is the junction of silicon and doped silicon to obtain a tip. And the measurements are quite complicated, as well as the description and interpretation of the signal. I will just briefly say about the interaction between the probe and the sample. This is a typical scanning probe microscopy. So our probe is in contact with the surface of the sample and scans its surface. Sorry for the Polish, I will translate it. So if the probe is in contact with the sample, we can observe the real mechanical contact. So we have a conduction through probe-sample contact. In ambient microscopes, there is also a very often problem with water. So we have a conduction through water meniscus, which is formed near the apex of the probe. And we have also convection and radiation. So a huge, complicated heat transfer of the heat from the probe to the sample. And there is no simple theory which allows for description of this interaction. So we use some electrical analogs. We describe this interaction in the form of effective thermal resistance of this contact. And we see here the connection, so-called resistors, corresponding to the solid interaction, interaction through air, interaction through water, and through radiation. And we can rewrite it as a thermal conductance. So we can sum thermal conductances describing each of these channels. And this is the method I used in my measurements. I studied selected oxide materials to characterize thermal conductivity and to check how we can modify thermal transport and how we can modify thermal properties. So the first group of samples, it was the barium titanate thin film. The thickness of the layer was about 100 nanometers, and some layers were annealed at 600 degrees for 1 hour. And I did some topography imaging and scanning thermal microscopy measurements. As we can see here, the layer as deposited was built from densely packed small grains. And after annealing, we observed formation of larger structures on the surface of the layer. And it was reflected also in thermal properties. The thermal conductivity was a little higher for layer annealed comparing to the as deposited one. And also the changes in morphology were very significant. After annealing, the roughness of the surface decreased and the mean grain size area was almost doubled. The next group was zinc oxide samples. We had layers deposited with the ALD method. We used two temperature of the substrate during the deposition, 100 degrees and 200 degrees of Celsius. And the thickness of the layers was dependent of the number of ALD cycles. So we had layers from 15 nanometers to more than 100 nanometers. And we investigated two groups. One was deposited at lower temperature and the other one was in higher temperature. But we kept the similar number of deposition cycles. So we started with investigation of the structure of thin films. Here you can see XRD investigations. You can easily notice the typical zinc oxide peaks. However, layers deposited at T1 were slightly different because the reflection from 002 plane was dominant for the whole group of samples, especially for thicker layers. If we look into the other graph, we can see that some the preferential growth along the 002 direction was disrupted, and the signal from 100 plane started to dominate, which is especially noticed for the thickest layer. This is the blue curve, the blue spectra. And we can say that there was some kind of transition from thin layers composed of small, densely packed grains into layers with larger, elongated grains. Applying the Debye-Scherrer formula, we were able to calculate the mean grain size, what we did. We also did some topography imaging, and you can easily see that the formation of bigger grains along with the increase of deposition cycles. In case of layers deposited at higher temperature, we had also one sample doped with aluminum. This is the last image when we see a quite elongated grains. This is the effect of doping. And if we gather all topography and structural parameters in the table, we can conclude that the roughness of the layers deposited at T1 temperature is higher. So it means that maybe the orientation of grains is different. And the same with the mean grain size. In case of layers deposited at T1, we have lower values for all layers. If we compare it to layers deposited at higher temperature, we have the bigger grains. So analyzing this data, we propose some growth mechanisms of these layers. So we can say that similar nucleation started in both groups of samples at the beginning of the process. So we have the typical island nucleation. However, with the increase of deposition cycles, we observed that grains vertically oriented were dominated the layers deposited at T1, resulting in some kind of spikes at the surface, and that's why the higher roughness. And in case of T2 layers, the layer by layer growth was dominating with the increase of the cycles. It means that the grains were parallel to the substrate, and that's why the roughness was slightly lower. We measured also the thermal conductivity, the electrical conductivity of these layers, and the values are gathered in the table. So we see here the electrical conductivity is here in kilo Siemens per centimeter. So it's from 0.17 to 0.7 doped layer. We have in the next row, we have thermal conductivity. And we see that thermal conductivity increases with the increase of deposition cycles. It means with increase of layer thickness. So the thinnest layer had thermal conductivity around 0.3, and the layer doped with aluminium, we got 4.3 watt per meter Kelvin. And applying the Wiedemann-Franz law, we were able to determine the electron and phonon component of total thermal conductivity. And results are presented in this graph. What we can see, the total thermal conductivity measured by scanning thermal microscopy, this is the blue dots. And we see that electron part is quite low in case for all layers. So we can conclude that in these polycrystalline zinc oxide layers, the phonon heat transport dominates over electron heat transport. And we did also some correlations. We see that the temperature induced some changes in orientation of grains. Here we have the mean grain size dependent on the thickness on this lower graph. We see that the mean grain size increases, and grains in parallel to the substrate were dominating in T2, thickest layers, and vertically oriented grains dominated in T1 layers. Having the mean grain size and thermal conductivity, we were able to calculate the grain boundary resistance. This is the last parameter, RTH. And we found that this parameter decreased with the increase of layer thickness and increase of mean grain size. We had for thinnest layers, it was about 5 multiplied by 10 to minus 8 meters squared Kelvin per watt. And the same was for T2 layers. We started with 6.7, and the thickest layer, that's the lowest, 1.3. It means that the thermal resistance decreases while the mean grain size increased. So there was a smaller number of barriers for phonons. That's why this parameter decreased. And we proposed some heat transport mechanisms. We can say that polycrystalline films composed of small grains, if we compare size to the mean free path of phonons, are considered as highly disordered structure, and the heat is conducted as a phonon hopping between neighboring grains. So we applied a Hartmann model to determine the grain boundary resistance. So we can say that the effective thermal resistance of the thin film is defined as the sum of thermal resistant of bulk materials. In our case, this is zinc oxide, and resistance from grain boundaries, and which we were able to calculate this parameter. And this is in this picture, we can see the hot thermal tip in a contact with the surface of the film. And the last group of samples were indium tin oxides. This was a very interesting group of samples because they were annealed at various temperatures in air, oxygen, nitrogen, carbon dioxide, some mixture of nitrogen and hydrogen, and vacuum. And we analyzed the temperature-induced changes in structure, electrical, and thermal properties of indium tin oxides. And we can see here some results from AFM studies. We see that the first one is reference sample. S2 is the sample annealed in air. S3 and S4 are samples annealed in nitrogen and oxygen. So the quite unique is the sample number 2 because we see some kind of texturization. We see elongated grains which are parallel in some kind of directions in the layer. And annealing in nitrogen and oxygen affected also in change of shape of grains. From elongated ones, we got some more rounded grains. And also the grain size changed. Yeah, we had a little higher grain size in case of reference and air treated sample, and lower mean grain size in case of nitrogen and oxygen. We did also XRD studies. We see here in this graph a typical reflections observed from indium tin oxide. And if we look into these small graphs, we can study how temperature influenced the structure. So here on these two graphs, we have the peak 2, 2, 2, from the plane 2 to 2. So the dominant. And we can observe that in case of reference sample, in case of sample annealed in nitrogen-hydrogen mixture, and in case of sample treated in oxygen, we can see degradation, a slight degradation of structural properties because we see the lower signal. Then we we measured also thermal conductivity of these layers applying scanning thermal microscopy. Here in this graph, we can see thermal signal as a function of thermal conductivity. This is so-called calibration curve to calibrate our probe. So we measured the signal for reference material with well-defined thermal properties. This is the curve with black dots. And then we measured indium tin oxide layers. And the experimental results are in the form of white squares on this graph. So for selected layers, we got values around 5 to 10 watt per meter Kelvin. The reference sample had the lower thermal conductivity, and the air-treated sample had the highest thermal conductivity. We also calculated the electron and phonon part of thermal conductivity, and we can say here that the electron transport dominates over the phonon transport in case of indium tin oxide layers. However, this tendency was shifted in case of the layer annealed in air, when we observed some kind of texturization in layer. Then we did also electrical measurements. Here you can see the graphs presenting electrical resistivity, concentration, carrier concentration, mobility, and Seebeck coefficient and power factor. We can see that annealing from room temperature to 400 degrees we don't observe changes up to 300 degrees. But if we analyze data for 400 degrees, we see that the electrical resistivity was almost double for layers exposed to oxidizing atmospheres. So the electrical conductivity dropped for layers annealed in air, oxygen, and vacuum. And similar tendency is in carrier concentration and mobility. So we can say that only the carbon dioxide atmospheres prevent the degradation of layers. And if we see on this graph with thermoelectric parameters, we can say that annealing in air and vacuum slightly improved Seebeck coefficient and power factor. However, layers annealed in oxygen and nitrogen had the Seebeck value almost the same as reference materials. And finally, my conclusions. So this was some kind of fundamental study of thermal properties of selected oxide thin films. We can say that barium titanate layers had the lowest thermal conductivity, and we can observe this quite strong temperature impact on the structure and thermal conductivity. In case of zinc oxide, we had a polycrystalline layers, and we could modify the growth mechanisms applying a different substrate temperatures during the deposition cycle. So we observed here the grains vertically oriented for T1 layers and grain parallel to the substrate in case of T2 layers. The thermal conductivity for zinc oxide thin films was in range 1 to 5 watt per meter Kelvin and increased with the increase of layer thickness, and phonon transport dominated, especially for thicker layers. And the last group of samples, indium tin oxides, they had quite high thermal conductivity from 5 to 10 watt per meter Kelvin, and increase of thermal conductivity was observed also. The largest value was found for sample annealed in air. And we observed also degradation in the structure and electrical properties for layers exposed to oxidizing atmospheres. And we can conclude that material engineering and also post-processing applied is a good way to modify phonon and electron transport mechanism to obtain enhancement in thermoelectric properties. And I would like to thank the group in Poland, Department of Applied Physics, and also my colleagues from Department of Physics in Oslo University, and also Dr. Jay from your university. Thank you very much. Thank you for your attention.
Thank you, Dr. Anna, for a very nice talk and introducing us into the fields of thermal transport in oxides and also scanning thermal microscopy. I'm pretty much sure we have learned something, and I hope audience have many questions. And now the floor is open for discussion.
Thank you, ma'am, for your nice presentation. Ma'am, I am having one question. By which technique you have deposited this thin film? You have deposited barium titanate and also zinc oxide you have explained. Can I know the technique? PVD, CVD, or which technique, ma'am?
Oh, I couldn't hear the whole question.
You didn't get my question, ma'am? By which technique you have prepared this thin film, ma'am? You have prepared one thin film and you have quoted all the parameters regarding that. So what is the technique behind it? Physical vapor deposition or chemical vapor deposition or solution method? By which method you have prepared this one?
She is asking which technique you have used to prepare the thin films.
Okay, which techniques, yes?
Yes.
In case of barium titanate, it was just a sputtering, DC sputtering,
Okay.
and we got 100 nanometers layers. In case of in the zinc oxide, we used atomic layer deposition method.
Okay, ma'am.
And in case of indium tin oxide, they, they were just commercially available layers. We didn't fabricate the indium tin oxide.
Okay, ma'am. Thank you, ma'am.
Thank you.
Any more questions? If we don't have any more questions, let's thank all our invited lecturers in this session.
Thank you very much. Have a nice day and goodbye. Bye-bye.
Thank you, ma'am, for sharing your deep knowledge about with us. And I thank Dr. Kalpana Singh on behalf of the SWAP organizing team for sharing your session, sir. Now we move on to the session oral presentation. We have only one participant. Yesterday they missed the session. So now he present his presentation. For oral presentation, you have only 8 minutes. Please stick on to the time. Thank you.
Very good afternoon. This is Muthukumar, research scholar from SRM Institute of Science and Technology. I'm happy to present one of my recent research work based on 2D nano hybrid, which is useful to treat antibiotic detections. So the topic is metal-free hexagonal boron nitrate and protonated carbon nitrate, synergetically enhanced 2D nano hybrid, which is a sustainable and metal-free catalyst, which is used to treat sulfamethacin identification as an electrocatalyst. So I'm doing research under Dr. J. Arogya Selvi, Associate Professor. And just introduction about antibiotics, why we need to detect to ensure the food quality and water surface water technology. So it is need to detect antibiotics in the surface environment, so that it is very useful, because to ensure the food quality it is necessary to avoid such kind of effect like human body, like crystalluria, hemolytic anemia. It is necessary to detect. So for that we need to fabricate such metal free electrocatalyst. So this is objective of this study. We are choosing two-dimensional material. One is protonated carbon nitrate and another one is hexagonal boron nitrate. So there is no electrostatic interaction between the carbon nitrate as well as boron nitrate. For that reason, we just modify the surface of graphitic carbon nitrate using hydrochloric acid. So there is a negatively charged nitrogen atom. There is electrostatic interaction. No electrostatic interaction between these two materials. We using ultrasonication using protonation. Then the nitrogen atom is positively charged. Then the hexagonal boron nitrate with liquid phase exfoliated into nano sheet by using ethanol and water, and it is negatively charged. So further it will be modified with surface modification by electrostatic self assembly between the two layers by stacking interaction. So we can get the hexagonal boron nitrate and protonated carbon nitrate nanosheet vertically aligned with the composite. Then the modified electrode was used to treat the sulfamethacin identification. So next, the characterization, the synthesized material further confirmed by different characterization, like crystalline nature of the material is confirmed by XRD analysis, and surface functional group is confirmed by FTR analysis. And the surface functionalities and binding energy, oxidation state of the material were confirmed by XPS spectrum and deconvoluted spectrum, showing the successful formation of the composite by using surface morphology of surface functionality is confirmed by XPS technology, and the surface morphology is confirmed by HRTM images, and the successful formation was confirmed by another EDS spectrum by all the element present in the individual spectrum. Here the HBN's nanosheet was observed as a 2 nanometer, and the D space value is calculated 0.2 nanometer, and the corresponding D space values correspond to the 002 plane of hexagonal boron nitrate, and also protonated carbon nitrate also 002 plane, and the two individual spectrum of 002 plane of hexagonal boron nitrate and protonated carbon nitrate present in the individual spectrum of composite, and also the hexagonal phase of boron nitrate is confirmed by SAD pattern, and the electrochemical characterization confirmed by the conductivity of the material. Here the electrochemical impedance spectroscopy is showing the high electrical conductivity of the composite material, and the anodic and cathodic peak difference, the del EP value shows the other than all the electrodes, the composite modified blue electrode shows better del EP peak to peak separation, and also the histogram showing the lowest RCT, that is charge transfer resistance, which shows lowest RCT value will give high conductance of the electrolyte. And electrochemical characterization of using the analyte, that is sulfamethacin and sulfonamides. The bad GCE shows peak around 0.95 electron volt, and means the current, there is a low current density, but the individual modified electrode with a different modified electrode by using hexagonal boron nitrate and protonated carbon nitrate, all the modified electrodes showing a very low current density as well as high potential, but the composite modified electrode showing potential around 0.8 volt with a high current density, which shows a better catalytic activity compared than other electrodes. Then the modified GC shows the better electrode versus current density as well as potential. The composite, this one shows lowest over potential around 0.8 volt, but the current is very high compared than other electrolytes. The histogram also shows the current is minus 23.63 microampere, which shows the better catalytic activity of all the modified GC electrodes. And the scan rate and pH of the electrolyte and in the presence of analyte is very important and crucial to optimize. For that, we optimize the scan rate as well as the pH of the electrolyte. Here the phosphate buffer electrolyte from in the presence of 100 micromolar of analyte, we analyze from 3 to 11 pH, acidic to alkaline medium. There is no drastic changes in the current response as well as the potential, but there is a huge difference in the pH of 7.4 and 7. You can see the current response of different pH levels, 7 and 7.4. There is much difference in the current response, but in the case of potential 7.4 and 7, 7.4 showing 0.82 over potential reduced than 0.84, which is very low. So based on these results, we optimize 7.4 is optimum pH level of the electrolyte. And the electrochemical analytical performance of the electrolyte confirmed by differential pulse voltammetry as well as chronoamperometric method. So determine the chronoamperometric method, we can detect the antibiotic as well as the many metal ions up to nanomolar level. So the response time which is very less than 2 seconds, which confirm the presence of analyte, which is able to detect our proposed catalyst, able to detect up to nanomolar level with a low response time. And the electrochemical characterization shows the mechanism of the reaction, how the antibiotic reacted with electrode surface, modified electrode surface. This is classic carbon electrode. We modified with our material, that is a metal-free catalyst. And the aromatic NH2 group, which is oxidized to hydroxylamine. We have 2 electron 2 proton process, which is confirmed by Leverron equation by using effect of pH and scan rate method. And another important factor, selectivity of the sensor is very important. For that reason, we optimized in the presence of analyte, antibiotic, with various biomolecule as well as metal ion and antibiotics. So there is no significant changes in the current response, showing the better selectivity towards the sensor. And also amperometric response, first we addition of sulfamethacin, the antibiotic, there is a peak with 1.5 microampere. But after the addition of various interferon molecules, there is no changes. And addition of another 100 micromolar of sulfamethacin, there is a huge difference in the current response, showing this sensor is more selective towards the sulfamethacin antibiotics. And from this, I conclude our proposed electrocatalyst sustainable and metal-free and easy to fabricate, which is the detection ranges from 10 nanomolar to 220 micromolar, and also the huge current sensitivity, which is 1.8 microampere, and lowest LOD, detection of limit 2.9 nanomolar. So synthesized material will characterized by different materials, different characterization like XRD, FTR, Raman, XPS, HRTM, SEM, and electrochemical properties was confirmed by cyclic voltammetry, electrochemical impedance spectroscopy, differential pulse voltammetry, and IT curve techniques. And also the optimum parameters we will confirm. pH 7.4 is very suitable, and electrolyte is phosphate buffer saline, which is neurological pH, which is very suitable. And also the catalyst ratio also we optimize, which is 1:2 ratio will show the better catalytic response. And also catalyst loading 6 microliter and applied potential 0.8 volt is giving good response. Thank you. And thank you very much for giving me the opportunity, especially to Dr. Annaraj sir for giving the opportunity. Thank you.
If you have any questions, you can ask now.
I'm very happy to answer any questions from the participants.
Maybe a question to both you and the whole audience.
Okay.
I have learned during this conference that there is a big need for a photocatalyst to oxidize all kinds of antibiotics and other compounds in water. Is there do we get new problems when we have all these materials in contact with water and maybe they spread in water? Can they lead to additional bad effects?
Okay.
Maybe you can answer if no one else wants to answer.
Yeah, actually the problem is the improper disposal and overdosage of antibiotics may expose to the surface water. So, and also to improve the food quality, it is need to detect first, then it need to degrade using photocatalyst or either electrocatalyst. Last time I can read on article to inject some injection they are using to grow the pork or meat, fish or meat something. So it may cause some health issue. So for that reason, it is necessary to detect antibiotics or some heavy metals something. Thank you.
Thank you.
Now it's a time for a lunch break. I would like to request all our participants and gets moved towards to the botanical garden. Meal is waiting for you. And after that lunch, we will assemble at Central Instrumentation Center at 2 o'clock. Our session, we have a session at 2 o'clock. Sorry, 2:30.